Very importantly, we need to look at the periodicity of elements. Periodicity of elements. What do we mean by periodicity of elements? Periodicity of elements. What does that mean? Now, like I told you earlier, when Mendeleev arranged his periodic table, he discovered that there were some properties that kept repeating. And with this repetition, he arranged those elements that have similar properties to fall into the same group. Okay, all the elements with the same properties fell into the same group, and that was how we got the groups of the periodic table. So what are those properties that vary across the periodic table? And for the sake of this course, we will be looking at 4 very important properties that vary across the elements in the periodic table, and those are atomic size, which is the atomic radius. You can call it atomic size, you can call it atomic radius. Then ionization energy, then electron affinity, then electronegativity. These 4 properties vary across the periodic table. Okay, but you will need to understand some things about the atom first to get to understand better how these properties vary across the periodic table. Number one thing we need to look at is that the proton in the nucleus and the electrons attract each other. The protons in the nucleus of an atom and the electrons revolving around the nucleus are oppositely charged, so they attract each other. And we must understand that the more the number of protons in the nucleus, the stronger the attraction. I take it again. The more the number of protons in the nucleus, the stronger the attraction on the electrons. That means if the number of protons increase, the electrons will be attracted more strongly, and that means they will come closer to the nucleus. As another proton is added, the electrons shift closer to the nucleus. So as the proton number increase, the electrons come closer and closer to the nucleus. That information is very important. Then we'll look at the second one, which is that the inner shell electrons in an atom shield the valence electrons from nuclear attraction. What does that mean? Now, there are shells. Atoms have shells, as we know. Atoms have shells. So what we are saying here is that the protons in the nucleus are attracting these electrons, but the electrons that are in the outermost shell are being blocked or shielded from the effective nuclear attraction of the nucleus. So the nucleus will have a stronger effect on the K shell more than it will have on the L shell, because the L shell will be blocking the K shell will be shielding the L shell. Okay, so as we move higher from L to M, the M shell is shielded by 2 inner shells. The N shell is shielded by 3 inner shells. So the further away the electrons are from the nucleus, the smaller the effect, or the smaller the attraction the nucleus will have on the electrons. Now, this blocking of valence electrons by inner shell electrons is what you call the screening effect. Okay, so we'll quickly also look at the third information we need to know, which is the size of an atom. The size of an atom. You need to understand that the size of an atom depends on the distance between the valence electrons and the nucleus. The valence electrons and the nucleus. And the further the valence electrons are from the nucleus, the less effective nuclear attraction. What I mean is, the electrons that are closer to the nucleus will feel the attraction of the nucleus more than those that are further away. So the further an electron is from the nucleus, the less the attraction. Now, having said this, we need to start looking at these periodic properties one after the other. The first is atomic size. We're going to look at atomic size or atomic radius. What exactly is the atomic size? What is the radius of an atom? What's the atomic radius? The atomic radius of an atom is half the distance between the nuclei of the atoms covalently bonded. When 2 atoms are in covalent bonding, the distance between their nuclei when you share it into 2, when you divide it by 2, you will get the radar. So how does atomic size vary in the periodic table? Now let's look at the periodic table from left to right. Across a period, the atomic number increases. For example, in period 3, sodium, magnesium, aluminum, silicon have atomic numbers 11, 12, 13, 14 respectively. That is to say that the nuclear attraction in magnesium is greater than the nuclear attraction in sodium. The nuclear attraction in aluminium is greater than the nuclear attraction in magnesium. The nuclear attraction in silicon is greater than the nuclear attraction in aluminum. So the nuclear attraction increase. What did we say will happen when the nuclear attraction increase? The size of the atoms will decrease. Again, why is the size decreasing? Because as the nuclear attraction increase, the valence electrons are pulled closer and closer to the nucleus. And when these electrons are pulled closer and closer to the nucleus, you notice that the size of the atoms as you move from left to right will decrease. So in period 3, for instance, sodium is the largest. Argon is the smallest. Are we together? Argon is the smallest because it has the highest number of protons within that period. Okay, so when we go down a group, on the other hand, down a group, the number of shells increase. The number of shells increase. Now, the more the number of shells, the more the screening effect. You remember what the screening effect is? That means more shells inside the atom are shielding the valence electrons from the effective pull or from the effective attraction of the nucleus, and that is going to make the atoms to get bigger, isn't it? If we look at group 1, for instance, lithium has only 2 shells. Sodium has 3 shells. So sodium is going to be bigger than lithium. Potassium is going to be bigger than sodium, so the sizes will keep increasing. So in group 1, the largest is francium. Francium is the largest in group 1, and the smallest is lithium. Notice I didn't say hydrogen. Later we're going to talk about the position of hydrogen. So the smallest in group 1 is lithium. Okay, so that is that. So generally we can say that atomic sizes decrease from left to right across the periodic table and increase from top to bottom in a group of the periodic table. Okay, so across the period, what is more effective is the nuclear charge, while down the group, what is taking precedence is the shielding or screening effect as a result of increased number of shells. Okay, we'll quickly look at ionization energy. Ionization energy. Now, ionization energy is the energy needed to remove the most loosely bound electron from a gaseous atom or ion. So, for an element like sodium, the ionization energy is given as is represented by the equation you can see on the screen. Then there is first ionization energy, there is second ionization energy, and there is third ionization energy depending on the element we are discussing. So there are some metals that can give off only 1 electron. There are some metals that will give off 2. Okay, so the metal that will give off 2 will lose 1, then lose the second. So the second ionization energy is the energy needed to remove the most loosely bound electron from the valence shell of a gaseous ion with +1 charge. Notice that this time around we are talking about an ion, meaning that it must have lost the first electron. The loss of the first electron, the energy needed to lose the first electron, is what we call the first ionization energy, while the energy needed to lose the second one is what we call the second ionization energy. And I'm sure you can guess what the third ionization energy will be. Now, the ionization energy of an atom is affected by some factors. Now, the first one is the distance, like we talked about before the distance of the outermost electron from the positive nucleus, then the number of protons in the nucleus, then the screening effect. I usually love using this example to explain ionization energy, and that is a hen and her newly hatched chicks. When a hen hatches, she keeps her chicks under her wing. It's a very it's a very funny and of course beautiful experience. They keep their chicks under their wings to protect them from hawks and other predatory birds that are flying about. And the truth is that the closer this chick is to the hen, the more difficult, the more energy the predatory bird will need to pick the chick. So what am I trying to say? The closer the electron is to the nucleus, the more the ionization energy. Remember, the ionization energy is the energy needed to remove the most loosely bound electron. And of course, these chicks from time to time begin to exercise their little legs. They want to hop up and down, they want to pick food, and they stray further away from their mother. And as they stray away from their mother, they are increasing their chance of being lost. So the further the distance from the mother, the lower the energy needed to pick them up. So it is easier to pick up a chick that is further away from the mother than a chick that is right under the mother's wing. So the further away the electrons are from the nucleus, the easier they are removed. Okay? So across a period from left to right, the ionization energy of the elements increase. Now, this increase is due to the increase in nuclear charge. Increase in nuclear charge, because from left to right the number of protons increase. And when we say nuclear charge, again for emphasis, we are referring to the number of protons in the nucleus. As the nuclear charge increases, the electrons are more strongly attracted to the nucleus, and as such more energy is needed to remove them from the atom. It is important to note also that the increase in ionization energy across a period is not smooth. It's not smooth. The first ionization energy of aluminium is less than the first ionization energy of magnesium. We expect that the first ionization energy will increase, but there is a decrease, and the reason is because it is easier to remove a single electron from the 3p1 shell of aluminium than to remove an electron from the paired 3s2 electrons. Okay, so if you read further on that, you're going to see that. So down a group of the periodic table, ionization energy decrease. Now, this decrease is due to, increasing shielding effect. What is responsible for the shielding effect again? The increase in number of shells. Good. The increase in number of shells. So as we go down the group, the number of shells increase. And of course, this increase in number of shells will lead to increase in shielding effect. And of course, it will increase the size of the atom. So in group 7, for example, group 7, the first member is fluorine. Fluorine is the smallest, Then, of course, chlorine is bigger than fluorine. Bromine is bigger than chlorine. Iodine is bigger than bromine, and so on and so forth. So their size increase as we go down. That's the same thing for all the groups. So quickly move into electron affinity. Electron affinity. Electron affinity is the energy given off when a gaseous atom gains an electron to form a negatively charged gaseous ion. Now I want to make something clear here. When an atom gains an electron, energy is given off. Energy is given off. Now, the higher the chance or the higher the tendency of an atom to gain electron, the higher its electron affinity. That is to say, the more electron hungry an atom is, the higher its electron affinity. We know halogens to be highly electron loving, as in they love electrons so much. They need just one electron to complete their shell. So they easily get electrons. They easily acquire electrons. Now, because of that ease with which they acquire electrons, their electronegativities, their electron affinities are high. They have high electron affinity. If we go to metals, metals usually prefer to lose electrons than gain electrons. They prefer to lose electrons than gain electrons. So it means that for metals, they will have lower electron affinity since they do not readily gain electrons. Okay, so if we look at group 3, along period 3, we'll see how electron affinity vary across a period. From left to right, electron affinity will increase because as you move from metals to non-metals, you are moving to increasing tendency of gaining electrons. So the period 3 have sodium being having less electron affinity compared to magnesium less than aluminium, and all the way to chlorine. And of course, we do not talk about noble gases when it comes to electron affinity, because noble gases do not they don't gain or lose electrons. So when we're talking about energy that has to do with gain of electron, they have no business in it. So we can say noble gases have electron affinity of 0. They have no electron affinity. Then down a group, the size of the atoms increase. I hope you remember that down a group, the size of the atoms increase. And if the size of the atoms increase, it simply means that the electron affinity will decrease, because the power to attract electron, the power to gain electron is in the nucleus. And because these are down a group, the size of the atoms increase, meaning that the electrons, the valence electrons, move further away from the nucleus. The size of the atom is wider and wider away from the nucleus. You will see that the chance that it can gain electron is very, very low. So down a group, the electron affinity decrease due to increased number of shells and increased size of the atoms within that group. Okay, so we'll quickly look at the fourth one, which is electronegativity. First, we need to know what electronegativity is. Okay, electronegativity is the ability of an atom to pull shared electrons to itself in a covalent bonding, pulling shared electrons to oneself, in a covalent bonding. And across a period, of course, pulling electrons to yourself means that you will need the nucleus to be close to the valence shell. That is to say, the smaller the atom, the higher its electronegativity. Okay, the smaller the atom, the higher its electronegativity. But that's not all. Not just the size. The proton number also matters. The proton number also matters. That means that if the atom is small with less proton, it will not attract electrons, shared electrons, as much as a small atom with more protons. Okay, so across a period from left to right, the nuclear charge increase. There is an increase in nuclear charge and consequently decrease in atomic size. You see, when there is increase in nuclear charge and decrease in atomic size, this will lead to increase in electronegativity. So across the period from left to right, electronegativity increases. When we go down a group of the periodic table, on the other hand, electronegativity will decrease. Of course, obviously, this is true because down a group, there is an increased size of the atoms. And the bigger the atoms, the less their electronegativity. Okay, I'm sure we understand that electronegativity has to do with size and charge of the nucleus. Then we also need to look at how electronegativity affects chemical bonding. How does electronegativity affect chemical bonding? Now, elements with high electronegativity usually attract electrons more than those with low electronegativity. So on the right side of the periodic table, the non-metallic side of the periodic table, we have elements with high electronegativity on the right side of the periodic table. Then on the left side of the periodic table, we have elements with low electronegativity. That's where we have the metals. So when an element on the extreme right, or on the right side, not extreme, sorry, noble gases are not part of it. So when elements on the right side of the periodic table combine with elements on the left side of the periodic table, because of the high electronegativity difference, the bonding is going to be ionic or electrovalent. Of course, ionic bonding is same as electrovalent bonding. So the bonding is going to be ionic. So because of the high electronegativity difference, the element on the left side of the periodic table will lose its electron totally to the element on the right side of the periodic table. Then if the elements have close electronegativity, as in their electronegativity values are not far apart, then they will engage in what we call covalent bonding. And you must also remember that the covalent bonding can be polar, and the polarity of the covalent bond also is dependent on the difference in the electronegativity. If the difference is reasonably high, the covalent bond might be polar. Then if the difference is not so much, then the covalent bond will be less polar. So that is that about the periodic properties of elements. Do well to ask your questions, whatever question you have, on the comments, and you will get your answers as soon as possible. Thanks for watching. Bye.